So now we can start talking about machine learning and how we can see the limitations of the behavior tree or rules-based algorithm be overcome using modern techniques. So before I get into what reinforcement learning is all about, it's first probably a good idea to tell you guys the basic building blocks behind reinforcement learning and neuroevolution. And one such example, one such building block is a neural network. So I'm not sure if you guys have heard of it, but it's basically so I think in that Morio video he did talk about this concept of neural networks. If you can probably see here. My internet is still bad. Okay, yeah, it's fine. So he did, if you recall from the video, he did talk about what neural networks are and how it was used as the brain of the artificial agent. And that's essentially what they are. They're basically like a mathematical way of how the human brain works. So here I have an example of a neural network playing Snake. So I'm sure you guys must have played Snake in your old cell phones and all that. So this is how a neural network actually looks like. And this is the basic building blocks of a basic building block of a modern machine learning algorithm. So you have, there are basically two important layers, one that you see right here and one that you see right here, the first and third layer. So the first layer is like your inputs. What does the robot or artificial agent see? And your last layer is basically your, oh, sorry, this is the last layer. Your last layer is your action. What can the robot do? So in Snake, you have basically four things. You can move up, you can move down, left, or right. And so these are your actions. These four are your actions. And as far as your inputs are concerned, this particular link gives a bunch of inputs, like where is the food located, how long is the snake, etc., etc. So yeah, so this is the basic building block of modern machine learning algorithms, and it's actually based on how the human brain also works. I've attached a few links to this in case you guys are not familiar with this, but yeah, this is a good starting point for you to delve into. Okay, so now we're going to talk about how the algorithms behind solving OpenAI and solving ModIO, that is that Morio example, actually work out. So simply put, the type of machine learning that is used to solve these problems is something called reinforcement learning. Okay, so this is actually based on behavioral psychology. So this is where the inspiration for RL came about. So you basically have a robot or an agent. We can call it an artificial agent. You can think of this like this particular bot as like Mario. And as Mario interacts with his environment, right, he basically sees a lot of things. So as he moves forward, he sees enemies coming towards him. So there is a constant interaction between Mario and the external environment. Now, how he performs in those interactions determines how well the algorithm proceeds. So what I mean by that is, suppose he gets killed by an enemy, then he basically gets punished. So this is how it works. The more good behavior that you end up doing, the more reward you get, and the more bad behavior or mistakes that you end up doing, the more you get penalized. And what the algorithm tries to do is it tries to maximize your collected reward. So, and then it propagates further. So that's what, so it happens on like a iteration by iteration level. So if you could recall from the video, at the first iteration, Mario just stood still, right? He couldn't do anything. But as the iterations progressed, he slowly figured out how to move to his right. Then he slowly figured out how to avoid obstacles. and sorry, enemies. And finally, he figured out how to reach the end goal. So that's how it sort of works out. It works in a sort of perpetual loop of taking actions, seeing how those actions ended up, what were the consequences of those actions, and then he gets either a reward or a punishment. So I'm not going to talk about how the algorithm actually works out. So it basically works on fine-tuning a neural network. So Mario's brain can be thought of something like this, a neural network. So I'm not going to be talking too much about that. I've attached links to that. But what I will be talking about is something called a reward function. So there are two components that you need to solve something like Mario. One is the actual algorithm itself, which people have developed. And the second thing is the reward function itself. So in a rules-based system, you basically provided the robot with a set of rules, right? With a set of if and then conditions. So how do we tell Mario to do something without explicitly telling him to do this or that? So that's where the reward function comes in. So if you can recall, so you basically have to reward good behavior and punish bad behavior. So in the context of Mario, this is how something would look like. So you give it some positive award for moving right, and if it decides to move left for some reason, you penalize it. And you basically also don't want it to stand still in one position, right? Because that means you won't end up progressing. So then you also would like it to kill enemies. You would not want it to die. So you place a large punishment for that, and you would also want it to complete the level as fast as possible. So you can maybe have like an exponentially decreasing reward for that. So that's what you should do. So this is your first step in solving, any decision-making problems using reinforcement learning. And this is the same steps that you have to follow when you solve each one of these problems. All right. So your first step is to first take note of what the robot can see. So in this particular example, let's take this. So in this lunar example, you have to think of what the robot can see. These will be your states. So that will be your first layer. What the robot can see is this layer. So for example, and what the robot can do is your final layer. So in this lunar example, what the robot can see is basically, if I recall correctly, I think it has its position with respect to the position of the center of the landing strip. And you also have force sensors. So you have sensors on its two legs that tell you how hard of an impact it's created. So once you have those sensors, you now have to think of what you can control. So in this particular example, you can control three things: your the thruster located down, the thruster to its left, and thruster to its right. So it's like a binary thing. When should I fire all these three thrusters, or should I not fire them? So once you have the states and your actions, or your inputs and outputs, then you can think of a fitness function or a reward function. So that is how you solve these problems. And once you have the reward function, you can basically just run the code and it'll solve it for you. But yeah, that's basically it. Any questions so far? Because I know that was a bit heavy, but I think you guys are capable to do this actually. So any questions? Okay, great. So yeah, so that's how you actually get started with solving complex reinforcement learning problems. And in fact, you can, it's not just related to robotics. Anything that you see in this world that needs some sort of decision making that needs to happen, and for problems that you don't need, that are too complex for humans to just write down rules, you can think of using reinforcement learning. And if you think that rules can solve them, then you can write up a behavior tree and it'll do quite well. So in fact, for simpler problems, it's actually better. It's more advisable to use something like a behavior tree, because these reinforcement learning algorithms take a very, very long time to train, because we're actually mimicking human evolution on a very small scale. So yeah. Okay, so with that, just a small recap of what we've learned in all these 6 weeks. So in lesson 1, we started off with studying how robots move, making them do simple turns, and that was the science of kinematics. Then in no, that was in lesson 2. So lesson 3, we also talked about sensing, how sensors are used to get data from the environment. And you can see in this particular example with OpenAI how important sensing is, because that's how you end up making decisions. So if your sensors are wrong, then you won't be able to make accurate decisions. Then we also talked about a little bit about control, how to make like a line following robot, and what are the advancements in control. And that's what led to today's discussion on intelligence. So you can think of intelligence as like the evolution of control. You can make control do simple things like following a line, but if you want robots to do really complex stuff, then that's where intelligence comes in. And then we finally talked about motion planning, the whole question of navigation, and yeah. So I've attached a few links. So if you want to get started with the field of reinforcement learning, because I just touched the surface, I recommend you starting off with this ebook. So this is a book on optimization. And then I would like you to get started with genetic algorithms. So this is a particular algorithm of optimization. And this is used in neuroevolution, to be honest. And if you like this area of robotics, there's actually a name to this. This is called evolutionary robotics. And this is like a huge area of active research going on. And finally, as a final note, a couple of final notes. If you want to see my particular implementation of neuroevolution, you can have a look at this link. So yeah, that's pretty cool. And finally, you should definitely check out this particular thing, multi-agent hide and seek. So you can see what is the state of art in reinforcement learning. This is actually a very, very cool example, because you could see this is something similar to what we have done so far. But if you actually end up watching this video, you can see that these artificial agents become so good that they end up breaking the physics of the game itself. So yeah, definitely check that out.